Today I'd like to talk about solving POM-DPs with continuous action spaces. POM-DPs are a mathematical model to phrase all kinds of robotic problems with uncertainty, be it uncertain states, uncertain sensing, or uncertain transitions after the action has been selected. Unfortunately, there has been only little work on solving problem instances with infinitely many action options. At its core, action selection is a maximization problem. We try to find the action that maximizes the so-called Q-value function. The catch is, however, the Q-value function is unknown. The estimates we have for it are far too crude for gradient descent methods, and the estimates we have are also constantly changing. To solve this, we use a class of derivative-free optimization methods called general pattern search. At the core of that method is a stencil, like the one shown here, of finitely many points, 5 in this example. And in each step, the stencil gets transformed depending on which of the 5 points maximizes the objective function. All those transformations form kind of a decision tree where each branch stands for one particular action maximizing the current stencil. The advantage of using this tree is that as soon as the estimates change, it's only a computational cheap switch from one branch of the tree to another. Furthermore, we can prove mathematically that the tree converges towards a maximum of the true underlying Q-value function, even though we only used finitely many estimates at any point in time. With this method, we can solve problems that require accurate action selection. In this example shown here, the red robot needs to push the blue box into the green goal to the top right, and the position of the box is not entirely known. From the robot's point of view, it can be anywhere in the blue area. So as we see, the robot approaches the box, reducing the uncertainty, does the first shot, the goal is missed, relocalizes the box, approaches for another shot, and completes the mission. This method integrates well with existing methods, such as POM-CP or ABT. The source code is available for download. And for further examples and details, please come and see me at the interactive session. Thank you.
Okay, while the next speaker sets up, we can take a question or two, please.
Excuse me? So we know that there are also like Monte Carlo tree search algorithms that deal with continuous action space. For example, the progressive widening algorithm. How do your algorithm like compares against those family of algorithms? Like for example, those algorithms like randomly sample some discrete actions from the action space and add more and more candidate actions as you have more and more computation powers.
I have to admit, I'm not entirely sure which algorithm you're talking about, but basically the advantage we have here is that we actually use the continuous structure of the action space, so we don't randomly select anything. We don't randomly select actions, but instead we hope the Q-value function has some sort of continuity property, so there's a maximum, and we try to find that maximum.
Okay, thank you very much. You guys can clap. The next speaker is Emanuele Magrini. He's going to talk about motion and force in physical human-robot interaction.
Thank you for the introduction. Have a good afternoon to everybody. I'm a PhD student at Sapienza University of Rome, and I'm going to talking about control of a generalized contact motion and force. We have developed this work to improve our collaboration level of our framework for safe human-robot collaboration. In fact, during the interaction phases, the human may physically touch the robot anywhere along the structure, the robot structure. So the ability of controlling the contact point motion and force becomes a relevant robot feature. In our recent work, we have presented how estimate contact forces without an explicit force sensing device, using our residual-based method, and using a depth sensor to localize the contact point. Relying on this, we introduced two control schemes two control schemes that generalize the impedance and direct force control to a generic contact point location. For example, in this experiment, impedance control is implemented at any contact point, keeping the desired inertia equal to the actual robot inertia. And for this particular choice, only the localization of contact point is required. On the other hand, if we wish to modify the desired inertia, in addition, we need the estimation of contact forces. As you can see in the second video, different masses produce different transient behavior. In particular, bigger is the mass, longer is the transient, and bigger is the oscillation. In case of force control scheme, we have performed a preliminary experiment in order to show that it's not recommended try to regulate the force only in a fixed Cartesian direction. In fact, as you can see in the video, if I push along the y direction where the decided force is 15 newtons, the regulation works very fine. But when I push the robot along another direction, the robot will drift, performing a dangerous movement. So in order to have a test-compatible control, only the norm of the desired contact force is directly regulated, while the direction is changing according to the human-robot contact geometry. So thank you for your attention. I would like to discuss with you at interactive both. Thank you.
Is there a question?
So the task is defined as a force that you exert on the robot. That's when you say the task.
In case of force control,
Can you repeat can you repeat the question?
We want to regulate the contact force to a desired value.
Can you repeat the question? Because nobody heard it in the back of the room.
Sure. You asked to me how we define the force task. Yeah, now it's just a regulation. So we ask the robot to keep in contact with a human with a desired value of the force. If the human pushes the robot is compliant in order to keep the values constant. Otherwise, if the human tries to remove the hand, the robot go against the human in order to keep the same value of contact forces.
Okay, thank you very much.
Thank you.
The next presentation is by Elliot Hawks, and he's going to talk to us about grasping without squeezing.
Yeah, welcome. So I'm Elliot Hawks from BDML at Stanford University. So most grasping in traditional robotic grippers is done with normal forces. So, for instance, the gripper on the left, when it's picking up, it can wrap around the object, which allows it to apply normal forces to support the object. However, in the case on the right, we can't get around the object, and we're going to squeeze it to grasp it. Now, what's going on there is we're applying these normal forces, but it's actually the friction that's tangent to the surface that's holding the object and supporting the weight. Now, friction's great. It's reusable, it doesn't take power, it's controllable, so we can turn it on and off by this application of the normal force. It's fast, but it has a downside. Because we have to apply a normal force to squeeze, if your object is delicate, like let's say a ripe tomato or maybe a water bag, a water balloon, you can crush it or deform it. On the other, another downside is that, let's say I can't quite get to the sides of the object. If I'm picking up like this, the normal force is actually pushing the object away from me as I'm trying to hold it. So there's some alternatives out there. Probably everyone's seen the universal gripper. It's using vacuum and friction. Other options are tacky adhesives that basically you can stick onto a surface, and then you can lift it up with that, and then to release, you're going to peel it away from the surface. But the goal of our work is, can we get back to those properties of friction without the downsides of squeezing? So this is our gripper. It weighs 2 grams. It costs 50 cents. And to get it to work, you basically just set it on an object. Now to turn it on, all I've got to do is apply a load to it. And now I've got the ball. Turn it off, I release the load, and then the gripper, actually under its own weight, falls off. So what can you do with this? You can implement it into a gripper, or into a robotic gripper, so you can make a little bistable mechanism to hold the film taut. When it touches the surface, it collapses, allowing the film to conform, and you can grip. To release, you simply reset the bistable mechanism. It's fast as well. So you can throw a ball at it. It can, once the mechanism collapses, the film engages, the adhesive turns on, we can actually catch a ballistic object. Finally, we can pick up something like a half-filled bag of water. So since the gripper isn't actually squeezing, all it's doing is touching down to the surface, applying these tangent forces, and can pick up the bag without deforming it. So if you're more interested in the details, you can talk about the adhesive, the fabrication. We'll have some live demos, so stop by our interactive session after these talks. And with that, I'll take any questions. So it depends on the radius. It depends on, the question was what is the payload, and it depends on the radius of curvature and the material of the object. The material, in the one video we can show later, we're picking up a large PVC tube, which is about 2 or 3 kilograms. It has a diameter of about 10 centimeters. Yeah.
What about texture and objects?
Yeah, so again, it varies with texture. So the worse the texture, you have less adhesive in contact, and you get less total force. We have videos of picking up my dirty leather wallet. That's a fun one. But yeah, it varies with the texture.
Okay, thank you very much. The fourth presentation is by Michael Yip from Stanford, and he's going to talk about high-performance robotic muscles.
Thanks. So I'm going to be talking about high-performance robotic muscles made from conductive nylon sewing thread. And so what I want to get across today is that there's a remarkable property of conductive threads that when you twist them and you heat treat them, these coils, the coiled structures that form provide repeatable contractions that exhibit useful muscle-like behavior. So we're motivated by the possibility to have a cheap, commercially available, and high-performing robotic muscle that's electrically actuated. And the question we addressed was, what is the underlying dynamics models of this phenomenon, and how might we can use control techniques in robotics to achieve high performance? And so we identified 3 models that dictated the dynamics of the new actuator that involved the thermal, electrical, and mechanical properties. And with a variety of control techniques, we were able to achieve controlled rise times of 28 milliseconds. And as a comparison, a human twitch cycle occurs at 100 milliseconds and reaches about steady state at 300 milliseconds. So we're far surpassing those kind of performance levels. And furthermore, a peak power to weight ratio of 51 kilowatt per kilogram was achieved. And in comparison, humans have on average have a 0.32 kilowatt per kilogram power to weight ratio. So we're again 2 orders of magnitude above that. And so this, therefore, puts us towards possible use for animatronic devices. And so what we built was an animatronic hand with 5 digits. And the digits were actuated completely using these sewing thread actuators. And the useful properties of this meant that it was a biofidelic muscle. It was fast-acting. It was lightweight. It was very cheap because all it was sewing thread. And obviously had high power to weight ratios and was repeatable in control. And in this case, it was open loop control. And so this gives the idea that it's an accessible robotic muscle actuator. And so I want to kind of get across the idea that a simple piece of sewing thread can be used as a very powerful means of robotic motion. And so we're excited to see applications for animatronic limbs, robotic prostheses, and soft robotics. And so please drop by to see videos on the construction, performance, and also the robotic hand in action. Thanks.
Are there questions? Yes, please.
So because these are conductive nylon threads, they are electrically actuated using joule heating. And the thing about that is for prior SMA actuators, they would have a long heat diffusion. But with a low thermal mass of plastic, it actually acts much faster in this case. Thanks.
One more question over there. There's a microphone here, you can just...
So what are the payloads? How much energy does it consume? And you also mentioned soft robotics, so how compliant it is.
Maybe I'll address the first point in terms of how much energy it consumes. And so it depends on what environment you're in and what the environmental conditions are. So I'll give you an example. In just air, we look at air, water, and forced air. In air, it's about half a watt of power.
All right, thank you very much. The next speaker is Konstantin Tsotsos, and he's going to speak to us about observability, identifiability, and sensitivity.
Localization of a sensor platform could be considered a solved problem, depending on how much you can afford. In inertial navigation, there's a predictable dependency between performance and price, and the promise of visual aid to navigation is of better performance at a lower price. The problem with vision, though, is that performance depends on illumination, reflectance, and other factors that are outside the control of the agent. But even if vision was perfect, how well can we really estimate pose? Observability is a necessary condition for any algorithm to infer the true pose states in a dynamical model of a sensor platform. Absent observability, there could be infinitely many trajectories x that are indistinguishable given visual measurements y and inertial measurements u. It's a structural property of the model, and it does not depend on noise, which by assumption is uninformative of the state and can be assumed absent. Unfortunately, the inertial sensor biases v are unknown and must be identified. It's customary to include these in the state and to model their derivatives as noise. But while bias rates are small, they're not uninformative of the state. They're deterministically related, in fact, and so we can't simply omit them from the analysis. Instead, we consider them to be unknown inputs and study the set of indistinguishable states for some small but otherwise unknown input. If this set is a singleton, then we stand a chance to recover the true trajectory. Otherwise, no matter how clever the algorithm, we cannot guarantee convergence to the correct trajectory. Unknown input observability has been studied before, and our contribution is to explicitly compute the indistinguishable set as a function of inertial sensor quality and motion characteristics. This has revealed some very surprising conclusions. First, the model is not unknown input observable. And with these bounds, using the sensor characteristics and motion quality, we can say very interesting things, such as the better the sensors, the smaller the bound. The smoother the motion, the larger the bound. So given a use case and a typical motion characteristic, we can characterize the sensors necessary to guarantee performance requirements. To validate this analysis, we have performed repeated experiments with Tango and our own algorithm, which will be presented on Friday morning. As predicted by the analysis, the inertial biases converge to a set. Instead, the inertial biases converge to a set outside the sensor spec, but within the indistinguishable set. The endpoint drift of the system, comparable for our system in Tango, exhibits similar performance. This is a structural characteristic of the model, and even exists when visual tracks are persistent. So we have established that pose is not observable from visual and inertial sensors, and we've explicitly characterized the unknown input indistinguishable set and computed bounds as a function of sensor quality and motion characteristics, thus characterizing overall visual inertial fusion performance as a function of the use case and the sensor quality. Thank you.
So we have time for one very quick question while the next speaker sets up, if there is one. Okay, so thank you very much again. The next speaker is Satoko Abiko, and he's going to talk about a flight control system for a quad rotor system making a large altitude attitude change.
Okay. Thank you, Chairman. The topic of our research is to develop flight control systems of a quad tilt rotor UAV for large altitude change. So what is a quad tilt rotor UAV? Is that the UAV which has a tilting mechanism in each propeller to change the thrust direction to get more advanced maneuverability compared to the conventional quad rotor UAV. So the features of this kind of quad rotor UAV has independent position and attitude control, as you can see in the movies. And also the another good feature is to get high control performance around Z-axis or yaw axis. So actually there are several research related to our topic, but now then get the flight control system in wide range of attitude change, and also nobody succeeded to get the rapid attitude transition control system. So the purpose of our study is to establish an attitude transition flight control system in the wide range of attitude change. So if we said that the normal hovering system is a conventional flight, and if we pitch up the UAV, we call it as a perpendicular oriented flight. So the simply flight control concept is shown here. And in the normal condition, we can use just, for example, in the XY axis attitude control, we use just the difference between the thrusters. And for example, in the perpendicular conditions, we use the tilting angle to change the attitude control. So this is a final result we get in this example. And then we could achieve not only to keep the constant attitude, and also we can get the quite stable transition control system in the wide range, that kind of wide range attitude system. So thank you, that's it.
Questions? Are there any UAV people here? I think you guys may have a question. Yeah?
Yeah.
The cost of having extra mass and extra motors
For the mass or total mass, and we design it's like the ratio between thrust and the total mass is 1.75, and actually it's not such big difference between the conventional UAV and this tilted rotors UAV.
Thank you.
All right, thank you very much. Those of you who do not know how to swim are going to enjoy David's talk now. He's going to talk about how to learn swimming gaits with legs.
Thanks very much. Yes, so I'm David Meager, and this work is motivated exactly as Ali said by the fact that humans, sometimes don't know how to swim. They struggle in the water, but after a lot of experience and training, they can become, amazing swimmers like Michael Phelps that I've shown here. We'd like the same kind of behaviors to be available on our robots, where this aqua robot that I'm showing here can often struggle to swim when conditions change, even after we've been working on this for about a decade. So So our technique allows the Aqua robot to benefit from experience in the pool and improve its behaviors to be able to do these kind of beautiful motions. We based our technique around model-based policy search, where, as you can see here, the robot iteratively executes different policies, and we can improve the policies in very few iterations. That's done in these kind of methods by executing a policy and getting experience, using that experience to fit a dynamics model to the motion, and then by using the dynamics model, we can rapidly solve for the policy which will produce the next best motions. After running multiple iterations, we can see very nice swimming on the Aqua robot. Now, the big problem here that we found when we tried this was that the computation time scales with the amount of experience collected, and since Aqua is a high-dimensional, complicated platform, this often wasn't in real time at first. So what we tackled during our paper was to produce natural swimming primitives that generated force on our robot with less frequent interaction. That took the runtime from hours to minutes each time we needed to learn. We learned on a cloud-based parallelized architecture such that we could learn 10 tasks at once, keeping the robot always swimming in the pool while the cloud was churning away in the background. We also implemented a realistic simulator based on Gazebo so that we could learn before we got to the robot hardware. Our swimming primitives are based on the intuition that a kicking motion for this robot is the best way to generate force. And so we've made a parameterized leg command system that you can see here, which allows us to just send commands once in a while we generate smooth controls that allow our robot to swim. You can see in our results here, we've learned a corkscrew, which is a smooth rolling motion at a fixed depth using only 2 of the robot's flippers, sort of an extra challenge here. When the robot begins to swim with a poor policy, it's not doing anything like a corkscrew. It just flops to the side. After the experience is gained and the models begin to improve, you can see a small rolling motion starts to happen by iteration 3. By iteration 5, you see sort of a corkscrew motion, but the depth can't be maintained. And after just 8 iterations of learning with no prior knowledge, we can see the robot doing a very nice smooth corkscrew, notice again only with 2 flippers, and maintaining its depth. So this is the first time we've been able to do these kind of motions with Aqua in the pool or anywhere else. And I invite you to our booth for all kinds of different tasks that we've learned, both in the pool and in the simulator, as well as more technical details. Thank you.
Thanks a lot. Questions are invited by the audience. There is one.
Can you talk a bit about the feedback you received? How did you get it, and how did you define the trajectory?
So he's asking about the feedback, and we have sensors on this robot that are an IMU and a depth sensor. So we're reading from those 2 things at a fast frame rate and having a feedback-based policy.
All right, thank you very much. One more time, clapping. The final presentation is by Anka Dragan, and she's going to talk to us about movement primitives via optimization.
Thank you. Hi, everyone. So our work this year is on adapting a demonstrated motion. So say a user demonstrates a trajectory to the robot from some start to some goal configuration. Think, for instance, of some natural reaching motion for an object. Now, what happens when the start or the goal need to change, as they often do when, or they inevitably will, when the robot needs to generalize that learned skill? How should the robot adapt that demonstrated trajectory ID to the new situation? That was the question we set out to investigate in this work. And there are many robotics approaches that address this problem very well. A widely adopted one is dynamic movement primitives. So very quickly, the way DMPs handle adaptation is they cast the demonstrated trajectory as a spring damper system that's tracking a moving target. And then they break down that moving target into a straight line plus some deviation. Now, in a new situation, you have a new straight line. You apply the same deviations and track that using the same spring damper system. And so this adaptation process is instantaneous, and it works really, really well in practice. And when we looked at this more closely, we realized, hey, this is one instance of this larger family of trajectory optimization problems. And looking at DMP adaptation this way, provides us with a different perspective on this really successful algorithm. And then on the practical side, it opens up the space to this generalization to different adaptation processes that are all possible using the same exact framework. So a little bit about this framework. Think of adaptation as needing to find the closest trajectory to the demonstration subject to the new endpoint constraints. And the only trick here is that the notion of closest is measured by the norm induced by the inner product in the Hilbert space of trajectories. And so now this optimization problem has an analytical solution that's trivial to implement. And what it basically does is if the norm M is simply the identity, then you just correct the endpoints. But if the norm has off-diagonal elements, then you start propagating that correction to the rest of the trajectory in various ways. So different norms induce different adaptations. And we were able to prove that the DMP adaptation is really one instance of this. It uses one particular norm. We also observed that in practice, there are certain tasks that can actually benefit from using a different norm. A task with a loop in it is an example of that. And then we also showed that the robot can actually learn the norm from a few demonstrations. So it can actually learn how to do this adaptation if the user provides a few demonstrations. And we tested this out with pointing gestures. And so to wrap this all up, we formalized trajectory adaptation as Hilbert norm minimization. And on the theoretical side, this was a different perspective on a successful algorithm. On the practical side, it opened up the space to a family of possible adaptations that the robot can choose for or learn. Thank you.
Thank you.
How you're going to include in your picture also the presence of obstacles so that the new trajectory should avoid some local obstacles?
Right. So, very good question. Obstacles can be treated by adding an additional term to the optimization, right? So you say minimize this distance plus some additional term that actually handles obstacle avoidance. Yeah.
And what about non-holonomic constraints?
So you can add non-holonomic constraints the way you would in any trajectory optimization system, right? So we already have the start and goal constraints, but you can have additional, if your system demands additional constraints or has interesting dynamics, you can add those as trajectory-wide constraints on the trajectory. So we have a paper a few years back that deals with doing this kind of optimization using trajectory-wide constraints with projections.
Okay, thank you very much.
Thank you.
And thanks to all the speakers of this session. I would like to invite you to attend the interactive poster presentations of all the speakers now, which are going to be in this room. And I would like to also point out that at 5:30, James Kuffner is going to talk about a cloud-enabled shaky. So please make sure that you come back for that. Thank you all for coming to the session.